Transmission lines, wave velocity, series on transmission line theory, lecture number 1.50. A rich and varied terminology got developed in transmission line theory: balance, stub, resonant line, infinite line, etc., etc. These are all the terms that come into being in transmission line theory. In the present session, our focus is on understanding various terms we encounter in the study of transmission lines. Uniform lines, lossless lines, low loss lines, lossy lines. These are all different types of lines. Uniform line is one when R, L, G and C, these are primary constants of the line. When they remain same all along the length of the line, then that line is uniform line. Non-uniform lines are also there, but they are considered later after studying uniform lines. Lossless lines, when R and G both are zero simultaneously, then that line is called lossless line. In case of lossless lines, alpha, that is attenuation constant. Real part of propagation constant is 0. Low loss lines, when R resistance is small when compared to omega L and G is small, very, very small when compared to omega C, then that line is called low loss lines. All lines working at microwave frequencies or high frequencies, they can be considered as low loss lines. For these lines, alpha is nearly 0. Not exactly 0, but it is very small. Lossy lines, when R is not 0, G also not 0, then the line is called lossy line. For these lines, attenuation constant is not 0. Balance. What are balance? Balanced, unbalanced, which connects a balanced line to an unbalanced load. It's a device, transmission line device. Balance, this term has been coined from balance, unbalance. Circuit devices used to connect a balanced line to an unbalanced load like antenna or another unbalanced line such as coaxial cable. So this connection between balance and unbalance requires certain transformatory device. That device is called balance. Examples for these devices are transformer balance, bazooka balance. No, resonant line. What is a resonant line? Lossless lines terminated over short or open. These are resonant lines. The significant feature of resonant lines is they carry pure standing waves. What are pure standing wave? Let us suppose here is a line and it is open or short. It doesn't matter, or it can be, termination can be even pure reactance. Let us suppose wave is launched over the line. This wave travels, reaches the load. Now here the load is open circuit or short circuit or pure reactance. Then what happens? Open circuit cannot accept power. Short circuit cannot accept power. Reactance also cannot accept power. So in such case, what happens? This entire wave gets reflected. Now you have two waves over the line and amplitudes of these two waves all along the length of the line. They are same, of course, if the line is, when the line is lossless. The same amplitude waves now we have over the line traveling in opposite direction, resulting in interference and standing wave pattern. As the strength of the two waves are same, equal, at the points of destructive interference, the cancellation is perfect. So therefore, at nodes, the voltage level or current level is 0. So perfect cancellation happens when amplitudes of both the interfering waves are same. So when perfect cancellation is there, that standing wave is called pure standing wave. So in case of pure standing wave, V minimum is 0, I minimum is 0. If I minimum is not 0, V minimum is not 0, then it is impure standing wave. Non-resonant line. A line terminated over its characteristic impedance is called a non-resonant or flat or smooth line. These lines, non-resonant lines, carry pure traveling waves. The voltage and current over such a line are constant throughout its length. If it is lossless and decreases exponentially, if it is lossless, they remain constant throughout its length if it is lossless, and it decreases exponentially if the line is lossy. The resonant line is one which is terminated over open circuit or short circuit or pure reactance. Non-resonant line is one which is terminated over characteristic impedance. Stub. What is stub? It's a piece of transmission line whose input impedance is pure reactance. Normally, short-circuited stubs are used because open-circuited stubs tend to radiate. This is a short-circuited stub. This is open-circuited stub. If you use open-circuited stub, what happens is this open circuit tends to radiate. When radiation is there, it is no more a perfect open circuit. What is infinite line? It is a line of infinite length. Consider a line. Let us say length is L. If you make L infinity, then it becomes infinite line. It is characterized by absence of reflected wave, and the current over the line depends only on its characteristic impedance and not on termination. Velocity factor, another term which we need to understand the meaning. It is also called velocity reduction ratio. Velocity factor Vf of a dielectric substance or a cable is ratio of wave velocity in the substance or cable to velocity in free space. Let us say there is a cable. Wave travels with certain velocity. Certainly this velocity is not equal to velocity of the wave in free space. In free space it is equal to 3 into 10 power 8 meters per second. But here it is, most of the times it is 1 by root mu epsilon if we neglect conductivities and all that. So it is different. Velocity over the cable is different from velocity in free space. That ratio is velocity factor. It is given by usually 1 by root epsilon r, where epsilon r is dielectric constant of the medium. Notice this is always less than 1. No phase velocity. It is an important aspect. Actually, the title of this particular session is phase velocity or wave velocity. When a source is switched on to a line, a wave of voltage or current starts traveling over the line towards load with certain finite velocity. It takes specific amount of time called delay to reach the load. What is trying to tell is this is line. If you switch on source here, a wave starts traveling towards the load. It takes some time to reach load. That time is called delay. The speed with which wave travels is called phase velocity. What is the velocity with which it travels? It is phase velocity. It depends upon parameters of the line. It is phase velocity, V, also known as wave velocity. Formally, phase velocity can be defined as the velocity with which phase of the wave changes along the line. An expression for velocity can be derived from the basics. An equiphase plane travels a distance of one wavelength in the duration of single time period. Hence, the wave velocity is V equal to lambda by t. It can be manipulated further. V equal to lambda by t from the basics of wave theory. Multiply by 2 pi numerator denominator. We have 2 pi f, which is omega. We have 2 pi by lambda, which is beta. Note, by definition, beta is 2 pi by lambda. This also from basics. Anyway, what is beta? Phase shift per unit length. So how much phase shift the wave undergoes in a one wavelength? It is 2 pi. So lambda corresponds to a phase change of 2 pi in the traveling wave. So phase shift per unit length is phase shift 2 pi divided by lambda length. So by definition, beta is 2 pi by lambda. Wave phenomena involves repetition of some activity. This is the definition of wave. Wave, remember, in general, involves two repetitions. Repetition in time, repetition in space. Of course, these two repetitions are connected. Angular frequency refers to recurrence rate of activity in time, whereas phase constant beta gives reappearance rate of activity in space. Their ratio is wave velocity. From basic EM wave theory, beta is omega root mu epsilon. This is from electromagnetic field theory. Hence, phase velocity of a wave traveling in a medium with the constants epsilon and mu becomes V. We have seen V is velocity is omega by beta, but beta is omega root mu epsilon. So ultimately, what you have is 1 by root mu epsilon. This is according to wave theory. See, here is a line. To make the things clear, it is a line. So this is in a medium. Entire thing is in a medium, dielectric medium. If it is a free space, mu epsilon is mu naught epsilon naught. Otherwise, let us say it is everything is in a dielectric medium. Some dielectric medium, permeability mu, permittivity epsilon. In such case, velocity for the conductors over the line is given by this formula. This relation, however, is valid when dielectric is pure, conductivity is 0. See, this is the medium in which the conductors are there. This relation In fact, this relation beta equal to omega root mu epsilon, it holds good only when this is a perfect dielectric. Otherwise, no. In case of lossy dielectric, that is sigma not equal to 0, the phase velocity is dependent upon frequency, making the line dispersive. For low loss lines, however, dispersion is negligible. Wave velocity can also be expressed in terms of primary constants of the line. In case of lossless lines or lines at higher frequency, velocity over them becomes V equal to omega by beta equal to, in case of lines, lossless lines, beta. See, we all know this is propagation constant alpha plus j beta. Gamma is of course r plus j omega L multiplied by G plus j omega C. Now, by manipulating this expression, you can find what is beta. Beta is omega root LC when line is lossless. When R is 0, G is 0, beta becomes omega root LC. So, V becomes 1 by root LC. Note, this is transmission line theory expression. V equal to 1 by root mu epsilon is the expression for V from field theory. However, when losses are there in considerable amounts, R is not equal to 0, G equal to not 0, this relation has to be modified. So V equal to 1 by root mu epsilon equal to 1 by root LC. This is only for lossless lines. Wavelength. What is wavelength? By definition, wavelength is distance by which a wave changes 2 pi radians in its phase. The phase change in unit length is beta, phase shift constant. Again, by definition. Hence, wavelength over the line is lambda is 2 pi by beta, or beta is 2 pi by lambda. This is also one of the basic relations which we need to have in mind, particularly in case of load matching and all that. Lambda we encounter frequently. Velocity factor. The velocity factor VF of a cable is velocity reduction ratio. It is defined as ratio of phase velocity V to free space velocity. As already mentioned, we have already mentioned velocity factor. Mathematically, velocity factor is actual phase velocity by free space velocity. This is 1 by root mu or epsilon r. Usually, we use non-magnetic situations. Therefore, mu r is 1. Now, we consider a low loss line. Low loss line. What is low loss line? Line for which r is very, very less when compared to omega L, G very, very less when compared to omega C. This is a low loss line. For low loss line, what is Z naught? What is propagation constant? What is attenuation constant? What is velocity? All those things we are going to investigate. See, microwave lines, so-called microwave lines, telecom lines, all fall in the category of low loss lines. Z naught. Z naught by definition is R plus j omega L by G plus j omega C under square root. Now this can be expanded and binomial theorem can be applied. Binomial theorem can be applied ultimately to find Z naught equal to roughly root LC, 1 by root LC. Or you need not do this much also. Simply see R is very, very less when compared to omega L. So R, neglect R. G is very, very small when compared to omega C. So neglect this fellow. Ultimately you are getting 1 by root LC. Propagation constant. This is by definition propagation constant. So a little bit of manipulation. Bring j omega outside. J omega L from the first factor, j omega C from the second factor, and apply binomial theorem and apply approximations. So ultimately what you have is j omega root LC plus half R into root C by L plus G into root L by C. But we have seen L by C under square root is characteristic impedance. So I can write this one as R by Z naught, this fellow. I can also write this fellow as G Z naught. So gamma propagation constant is j omega root LC plus half R. Now if you replace it, so that is as far as propagation constant is concerned. But real part of propagation constant is attenuation constant. Imaginary part is phase shift constant. So real part you are getting alpha like this. This is phase shift constant. Attenuation constant can also be expressed for lossless line. It can be expressed as already mentioned. Root C by L is there. That can be replaced by Z naught. Root L by C is there. That can be replaced replaced by Z0. For air dielectric lines, G is negligible. G is 0. Therefore, you are left with half R by Z0. In this case, lossless line, low loss line case, V is roughly equal to, because omega by beta is the basic definition of velocity. The omega by beta, it is applicable for lossy lines, lossless lines, low loss lines. This relation is common to all types of lines. Whereas 1 by root mu epsilon or 1 by root LC, those expressions are valid for lossless lines. Right. If you implement this definition for low loss lines, it becomes 1 by root LC, which is same as lossless lines. Operation of lines can be classified into two categories. We come across balanced operation, unbalanced operation. Some information is being provided regarding these two types of operations, balanced and unbalanced. First, about balanced system. A balanced line usually consists of two identical conductors, each one having equal impedances along their lengths as well as ground. Both the conductors carry signal currents of equal magnitude but in opposite directions. So if one conductor carries current in one direction, other current carries current in the opposite direction, of course amplitude wise they are same. Any pair of wires can be operated in balanced mode provided that neither wire is at ground potential. Signal transmission over a balanced line reduces the noise and also interference. This is the basic thing, important thing, significant aspect pertaining to balanced lines. Reduces the noise. It reduces the interference due to external stray electric fields. Because we are in communications, so for us noise is the thing that requires our serious attention, that draws our serious attention to be eliminated. Interference, similar interference also. The interference affects both the conductors in the same way, and the noise due to interference is routinely removed at the load end by subtracting signal of one conductor from that of the other. Longer runs of lines are possible as balanced operation gives smaller amounts of noise per unit distance. Common examples are lower frequency twisted pair and radio frequency twin lead lines. Some more information regarding balanced system. Balanced lines are very often used with a differential signaling mechanism, and hence these lines are also called differential lines. Differential signaling refers to lines carrying symmetric signals, those with equal but opposite voltages on their conductors. However, differential signaling does not make a line balanced, nor does noise rejection in balanced cables require differential signaling. Here is shown after having some information regarding balanced operation. Now if you watch operation of a balanced line, within no time you can catch its significance. See, this is signal source, this is load. Here is load. Now source is connected between these two conductors. If it drives current like this in this conductor, the current is returned through the another conductor. That's why if it is sinusoidal, it is like this, and opposite. If it is plus, it is negative on the other side. Now at the other end, a differential amplifier is used. This differential amplifier subtracts the signal from one conductor from the signal that is there in the other conductor. In the subtraction, the noise that is attached, interference also, everything gets cancelled. Ultimately, of course, A plus A becomes 2A. Here it is shown. Output is A plus N minus A plus N. N gets cancelled, leaving behind strengthened, much more strong signal. This is balanced operation. In unbalanced operation, what happens is a source is connected between conductor and ground. Ground is used as another conductor. Signal travels like this. Here it gets amplified. While traveling, it catches certain amount of noise. This noise may be atmospheric noise, or it may be due to interference, or it may be due to temperature in the surroundings, or whatever it may. It catches some noise. Here also it catches in balanced operation also, but both the conductors catch same noise. Therefore, cancellation happens while passing through differential amplifier. Here there is no differential amplifier. It is a unity gain amplifier. So while passing through, not only signal gets, of course, unity gain, so no amplification, of course. Both signal and noise, both pass through the amplifier, comes out. Now output is signal plus noise. Here it is only, at least theoretically, here it is only signal, but here it is signal plus noise. noise. That noise is there. Whatever is attached while traveling through the line, that noise remains there. Now, how to remove this noise? It's a big problem, serious problem. So normally, these are used, unbalanced systems are used when noise is not a serious problem. For example, in case of small distance communication, or noise is not a problem. There are applications where noise is not that much serious problem. In such cases, unbalanced operation. Unbalanced lines are single-ended lines. Consists of, see some information regarding unbalanced system. It consists of two conductors, one to carry the signal and the other to act as a reference or return, called ground or common. Usually these lines are designed to have its return conductor connected to the ground, or the return conductor actually is ground. This is the most general situation. Ground is the return conductor. When ground is the conductor, part of the line, naturally all the currents that are there in the earth, currents, voltages, fields, so many electrical phenomena takes place in the earth, all those, they influence this conductor, resulting in creating a certain noise. So these are noisy. These lines tend to be noisy. These are noisy actually. As one of its conductors is at grounded, the probability of interference noise being induced is more compared to balanced lines. Unbalanced lines tend to have more noise per unit distance. As already mentioned, unbalanced system, unbalanced operation, we go only when noise is not much of a problem. It is not an issue. There are applications. In such applications, non-serious applications. These lines are capable of using only for short distances. With these lines, cable run between transmitter and receiver becomes highly restricted. Standard two-conductor coaxial cable is an example for unbalanced operation, as a second conductor or shield is generally connected to ground. So this is what I want to share with you regarding the terminology we come across while studying transmission line theory, while trying to understand transmission line theory, while we go for the design of transmission lines. Enough for